Oops. Okay, here you go. All right. All right, so what I'm going to do first of all is, let's say you know nothing. Let's say, well, that's pretty close. What I'm going to ask you right now is to just go down the row. We'll go down the row, and let's start over here on this side. I always start on this side. And all I'm going to ask you to do is, if I say nuclear anything, nuclear chemistry, nuclear physics, just give me a word that you said, oh, I'll bet we'll might look into that. What's something that comes to your mind when I say nuclear?
Energy.
What is it?
Energy.
Okay. All right, we'll go right down the row, and I'll try to write these as fast as I can. Next.
Einstein.
What?
Einstein.
Okay.
First thing that comes to our head, is that what you said?
What now?
Or just say the first thing that came to our head?
Yeah. All right, go ahead. Well, now you got to come up with another one. So I think the list is going to be like 30 words long. Say it again. Factories. Right?
A ball.
Fission and fusion.
Oh, you took somebody's. Right? A what, nucleus? And speak of it. I hate these maths, but help me a little bit.
Chernobyl.
Electrons.
Alpha beta particles.
You already knew about these? Next. Next. It's getting harder now because they took a lot of the good ones.
Electricity.
San?
Electricity.
Electricity?
Atoms.
Radioactivity. Hiroshima.
One more time.
Hiroshima.
Ah. Have you guys talked about that at all in any of your classes?
A little bit.
Okay. All right. Now, you could either say, if you think of one, go ahead and tell it to me, and if not, just say pass. I'll tell you what, to save time a little bit, just raise your hand if you do think of another one. How about that? Go.
E equals mc squared.
One more time.
E equals mc squared.
Ah. Ah. What else? Just raise your hand. Yes? All right. Everybody else, raise your hand. Just say, something came to me.
Even if it's not like scientific,
Say it again.
if it's not scientific, because we did one in like.
Well, yeah, it can be.
history, like little boy or something.
Little boy?
Yeah.
Okay.
Yeah.
Okay, the name of the bombs? Okay. Anybody else? Yes. Light? Okay. Yes.
Is it the mushroom cloud?
See, what's interesting about the, I'm actually from an era where, okay, in the 1950s, if someone said, "What's the biggest problem in schools?" You know, what's the biggest problem? It was chewing gum. What was the biggest concern in the 60s? Nuclear war. That's a little different, isn't it?
Yeah.
The principal was worried about people chewing gum, and then they're worried about kids being nervous about nuclear war. So in the 60s, it was something on people's minds. and there was a possibility of a nuclear war. I don't think you think about that too much, do you? Is that correct? And mushroom cloud, of course, that would have been something in my era that everybody would have known. But I'm surprised you even knew that. Where'd you hear about that?
We watched like a video. and
Oh, we watched a video. Ah, okay.
Chain reaction.
All right. What class did you see this on?
It's just
What?
We just studied how the bombs work for Hiroshima and Nagasaki.
Oh, really? Okay. In history?
Yeah.
Okay, that's good then. Yeah,
Chernobyl.
yeah, I got that one.
Oh, you did?
That's okay. Yeah.
Radium. I don't
Okay.
think-
Yep.
Radioactive isomers.
Isotopes.
Sorry.
Yeah, we gotta be careful because we just had a whole bunch of things on isomers, didn't we? But
Yeah, sorry.
now we're back in talking about the nucleus, and now we got isotopes. And I think I had that here. Did I have isotopes here? I thought I had that. Maybe I didn't. Yes. What?
never mind.
Okay. But yes.
Manhattan Project.
Okay. Okay. Yes.
Protons.
Photon.
Protons and photons.
Oh, proton. And photon. Anybody else? All right. So yes.
Lead maybe? Lead.
Lead has something to do with this. Yes.
X-rays.
X-rays. Wow, that's a lot, isn't it? That's a lot. And yet, we should be able to talk about all those. I probably won't get as much into the history as your history teacher would have. And I don't know, I wouldn't mind showing a video, but if you've already seen a video on it anyway, I don't know if I would do that. But I'd like to be able to show you the science behind that. And I can tell you right now, here's what you're going to have trouble with. See, that's what you're gonna have trouble with. Is nuclear chemistry good or bad? So that's gonna have trouble. And I'd be careful. In the history class, were they kind of showing how everything was bad?
Yeah, it was mostly just focusing on the bomb. They weren't talking about like nuclear power plants or anything like that. It was just the weapons of mass destruction.
Yeah, I bet almost everybody in this class knows somebody who had to maybe drink a material and it showed up on a screen. They had to look at something like their intestines, their stomach, and that was radioactive. That was a radioactive dye. And without that, they wouldn't have known like what the problem was. And so it saved many lives by being able to use that. So we'll get to that too. So what do you think? You ready to start? Yes.
Didn't they used to have like handheld devices where they like a handheld device where they can literally do an X-ray of someone just
I don't remember the exact time period, but it's probably in the 50s if I had to guess. They had a traveling truck that would go around and they thought they could sell, even at some shoe stores, they thought they could sell more shoes if you stood on this thing and they took an x-ray of your feet and they could tell exactly what size shoe you needed, and they thought that was the thing. And it was very scientific. Then I don't know when they shut down, but I'll bet they found out very quickly, we need to shut down and get out of here, because we've been shooting x-rays at people's feet, but they didn't stop at their feet. And we're going to be blamed for a lot of malformed babies. Because even when you go to the dentist, you know, they have you ever had x-rays? Okay, anytime you have an x-ray, what do they cover up? Your face? Your feet? No, they cover where your sex cells are, huh? Don't they put a blanket over there and say, whoa, I guess. Yeah, that's and so, for example, one thing you didn't talk about was mutations, and so you could have a mutation in a somatic cell, a body cell, and oh man, it died. Okay, another cell came to replace it, or maybe it's really mutated and it keeps growing. Like, oh, that's bad, and you got to get cut off. Cancer. But what if you have a mutation in your sex cells? So I know you know biology a little bit. So you know that the sperm cell has 23 chromosomes and the egg cell has 23, and the new life starts with those 46. And if any of those 46 are already damaged or mutated, then that cell makes copies of itself into trillions and trillions and trillions, and every cell in your body has that mistake now. That's kind of hard to fix, isn't it? 75 trillion cells, how are you going to fix that? So that's where you have to be careful about mutations. Yes?
Why does DNA have such a... is DNA just more susceptible to radiation than
Not necessarily. Radiation could break down proteins, but breaking down a protein, all right, so what? You don't have that protein to build something with. Okay, so it gets taken apart and put back together. But if you were to, a certain kind of mutation on the DNA would mean that every time I make messenger RNA, every time I said I want to make something, every time the instructions are changed, now you don't know how to make. You always make the bad thing. You always make this. You always make this. So I think that's why you hear about it more, because it has more. The results are worse. If I had a lot of cells making the wrong proteins and things, that could kill me. Yes.
One more thing to add to the list: Geiger counters or Geiger.
Geiger. A Geiger counter. Now, when I was younger, imagine using the bomb in World War II, and people said, "What was this? What was this? This is not like the bombs from before. It's not like dynamite. It's not like gunpowder. It's not like nitroglycerin. It's something different." And so nobody even knew what this stuff was. And so after World War II, in the 50s, that's when you started seeing this whole genre of movies and said, "Hey, X-rays, this is going to cause mutations." And you saw all these black and white science fiction movies where the 50-foot colossal woman, you ever see that? And all these movies came out because people said, "What is this stuff? Radiation? What is this stuff? Oh, it causes that? Ooh, okay." And you saw all kinds of movies, and Geiger counters would have been something I would have seen on TV all the time. Click, 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 you know. And you would have seen that in many, many movies because it was the thing in the 50s. People want to know what this was, you know. Okay, all right, that's great. That's a great way to start this out. Now, I want to tell you about some things that I didn't know. I didn't know any of this. None of this was taught to me in high school at all. So I didn't know anything about it, okay? I watched these movies. I love those movies. But anyway, here's something I want to talk about here. In chemistry, and so far all the chemistry you've known, what did the word stable mean when you were talking about an atom being stable? What do you remember? Yes.
Its outer shell and electrons are filled.
Right. That's right. And we'll talk about that again, but you're right. The outer, the valence electron shell is full. And so the most famous stable elements were the noble gases. Why don't you want to gain electrons? I'm stable. Why don't you want to lose any? I'm stable. Why does sodium only want to lose one electron? Well, you want to lose one, he'll have 10, and my electrons will be in that arrangement, and I want them that's stable. And so that kind of stable is different than you're going to read about now, because that is an atom being stable and meaning, hey, are you an active? Or do you want to do a chemical reaction? Not us, but we do. We do, because we can become more stable by either gaining electrons or losing electrons or sharing electrons. That's the chemistry you know. It's all about bonds, you know, stable atoms forming chemical bonds. You got that? And all the chemistry you've ever learned, ever, was electron chemistry. It was all about the electrons being stable. The electrons are stable. You get that? And maybe they're not stable until they form a bond with another atom. You get it? Then they're more stable. Now we have to take that off the table because we're not talking about that anymore. This chapter is a different kind of stable. This has to do with your nucleus. Okay? Which is nothing like the chemistry you've learned in the last 2 years. There's nothing like it. Now I want to know is, let's take a look at your nucleus. Just the nucleus. Hey, what do you do in nucleus? I'm carbon-12. Carbon-12? I'm very stable. 6 protons and 6 neutrons, that's very stable. The tendency for me to change into something else is very, very small. Very small. What about this guy? How about the carbon-14 nucleus? 6 protons, 8 neutrons. How about you? I'm not that stable. What do you mean you're not that stable? I might turn into something else. What do you mean? My nucleus is not stable. Well, what are you going to do? I might throw away 2 protons and 2 neutrons. What? I might throw away another thing. I might do something else. And why would you do that? To become more stable. And so if an element is stable, then that isotope tends not to be radioactive. It's not radioactive. But if you have a nucleus that is unstable and it tends to change, when it does change, it can have consequences, and that's called radioactive. So we have radioactive isotopes, and we have some that are more stable. Now notice I didn't use the word electrons, all right? So we're not really in electron chemistry anymore. We're talking about the chemistry of the nucleus of the atom. So I'm not going to talk about gaining or losing electrons and forming chemical bonds. We're going to talk about whose nucleus is stable. Okay, real quickly. 1 proton. Here's hydrogen 1. This is called protium. Remember protium? Okay, so protium 1, very stable, very stable. Here's another hydrogen isotope. Hydrogen 2, 1 proton, 1 neutron. Fairly stable, deuterium. This one, not. 1 proton, 2 neutrons. Not stable. What is it called then? Radioactive. Tritium. So of the 3 isotopes of hydrogen, 2 are stable and 1 is not stable. All right, now I'm not asking you to know all this already. I'm just saying at least get the idea of what I'm talking about. Every one of these elements has isotopes, all of them. All of them have stable, I shouldn't say that. All of them have unstable nuclei, isotopes. Some of them, that's all they have. Here, of the 3 isotopes of hydrogen, 2 are stable and 1's not. 1's radioactive. Here, of oxygen, there are 2. 1's radioactive and 1's not. But let's say right here, starting right here, anything past 83 and beyond, 83 and beyond, no such thing as a non-radioactive polonium. No such thing as non-radioactive uranium. No such thing. When you get to this point here, every isotope of every element is unstable, which means it's radioactive. Yes, no? Can you have a radioactive manganese? You can. You can. But there's also stable manganese, isn't there? But there is no non-radioactive astatine. No, every protactinium is radioactive, every isotope. Yes?
You may not be able to answer this, but as far as like percentage-wise, like non-reactive to radioactive, do you know for the ones that are not all radioactive isotopes? Do you know the stat for that, or is that
You mean the ones that are not all, the ones that
Yeah,
are,
like for every
below
100
83?
For every 100 oxygen atoms, how many of those are
Oh.
gonna be radioactive?
I might not know that. As a matter of fact, I don't know all the isotopes. I know hydrogen's 3 isotopes, but if you ask me how many isotopes of chromium, I have no idea. I had to look it up. So, and some of them might have 6, some might have 3, some have 7. I wouldn't know that. I'd have to look it up. Yes. Yeah. Okay, so you see where I'm going for this? Okay, all I'm doing is trying to tie in some of these words. Now, what happens to a nucleus that's not stable? Over time, it may decay. Now, again, since I never had this in, in high school, and I was very naive about lots of things, really. And if you said the word decay to me, I knew, I used to go outside all the time. I've gone in the woods. Oh, man. Ooh, that bird. Ooh, that was stinking. Ooh, it was decaying, wasn't it? That's the only word I ever knew. The only thing I ever knew about decay was stinky animals. Well, what kind of decay is that? That's electron chemistry. That's these little animals. That's these little organisms like bacteria and fungus, and they're breaking down the body of the animal and giving off an odor. But that's all electrons. That's the chemistry going on. See that? That decay has nothing to do with the nucleus. No nucleus is touched in a chemical reaction. But what do they mean by decay? It means, for example, let's do, you won't know one. Let's do uranium. See uranium? All right, uranium has 92 protons. Let's go this way, okay? Uranium, 235. I'll use that one because it's the most radioactive isotope of uranium, okay? Okay, now, this guy here, he's not stable. He's not stable. Matter of fact, no isotope of uranium is stable. And so what does it want to do? What's this nucleus do? I can't believe it, but he does this. He gets rid of 4 parts of the nucleus, and he gets rid of 2 protons and 2 neutrons, and they go away. They jump out of the atom, and they go and say, what? If uranium were to lose 2 protons and 2 neutrons, it wouldn't be uranium anymore. You are right. It would decay into another element. Now, the alchemists for a couple thousand years were trying to change one element into another. They could never do it because they were doing electron chemistry. See that? They couldn't touch the nucleus. Even dynamite going off doesn't do anything to any nucleus at all. So yet, we do know that you can transmute. You can transmute. As a matter of fact, that's called natural transmutation because by itself, it'll change into another element. But by the way, this element is also radioactive, so what's going to happen to that? It's going to transmute into another element, and sometimes you'll find out that elements jump down to, boink, boink, they lose 2 protons, and you know what's going to happen to their mass? If you lose 2 protons and 2 neutrons, I get it. The atomic number goes down by 2, but what happens to the mass? Down by 4. Ooh. But there are some other types of decay where the element does this. It goes from like here to here. What? What? How in the world did you jump up? I get it. If you want to throw away 2 of your protons, I get it. You jump down. But what about elements that can do whoop? Whoa! Yeah, you can't do that. Where'd you get that extra proton? Anybody have an idea? You're not going to like the answer. Matter of fact, you'll say, you're lying. You're lying to me. Where do they think a radioactive element that actually goes up, if they go up on the periodic table, where do they get that extra proton? You know? I'm listening.
Neutrons sometimes turn into protons.
Yes. If a neutron ejects part of itself, what's left behind is a proton. Oh, whoa, whoa.
So then is it losing any
Okay, all right. Even though we'll get the details in there, the answer is no, because what it loses is weighs the same as
So it stays the
an
same.
electron. All right. So anyway, I just want to give today's an overview, right? A little bit of overview. Yes.
Isn't depleted uranium a stable material?
Depleted uranium. If it's uranium, it's not stable.
Well,
Now,
that's part of the question.
If we will, and when we get to some of the details, you'll find that uranium goes through a decay series. I turn into this, and then I turn into this and this, and different isotopes have their own little pathway that they decay, and many of them, not all, many of them will stop when they get down and become lead. So many radioactive things will stop decaying when they get to a stable isotope of lead. That's why lead comes into play sometimes. Yes.
So whenever they they talk about, I think a lot of armored vehicles use depleted uranium on.
Okay, if I had to guess, then it must be mixed with other things, and so there is uranium in it, and it is radioactive, but uranium just happens to be very, very dense. So I'd have to read your article, but if I had to guess, I don't think it's because it's radioactive. I think it's because it's really dense. So if you can make armor that's really dense, it might tend to make some things not penetrate. I'd have to, if you want to bring that article, I'd like to read it, because I have no. When you say depleted, in nuclear power plants, they have rods, fuel rods that are made of uranium. But over time, the uranium changes into other elements. You see that? And when a percentage goes down from 100% uranium or whatever, 80, down to 10, maybe they have a name for that, depleted uranium. There's a little bit of uranium there, but most of it's not. Most of it's stable. So I'd have to look that up as far as armor. But it's pretty neat that somebody thought that might work. All right, what do you think so far? Are you interested at all in this? All right, so what I'm going to do is let's go to your packet here. And I'm going to cover this up because I don't want you to see that yet, okay? What we have to do is we have to learn some new vocabulary words. So that's not too bad. And we're going to also know some characters. And so anyway, by the way, have you seen this on TV? Like The Simpsons? No. You ever watch The Simpsons? Okay. Homer works at a nuclear power plant. Does everybody know that? A lot of times they start anyway, does anybody know what that is right there? Anybody know what this thing is? I used to live a place that had one of these, but it's called a cooling tower. Have you ever heard this before? How many people have seen one of these? Oh, good. Where were you at?
I was about Lake Erie.
Where?
Lake Erie.
Ah. Who else saw one? Yes.
There's one, I don't remember exactly what lake, but I went rowing for a regatta somewhere in North Carolina, and there was one right by a lake. I think
By
it
a
was-
lake.
it was
Ah.
maybe-
Okay. So let's say you see one of these, okay? And you usually see this white stuff coming out. Does anybody know what that white stuff is? Anybody know? Water. Oh, look at that. I'm polluting the sky. It's water. It's okay. It's water. Yes. Now, what do you need? I actually used to live next to one, and it had nothing to do with a nuclear power plant. And I lived in a place where they had day after day, trains would bring train cars full of coal. And I played softball a lot, and we had one softball field. It was right next to this huge mountain of coal. And every day there'd be a bulldozer, and they'd get some, and they'd take it somewhere. And it was just like Duke Power. And that's what Duke Power does. Duke Power takes coal, and it burns it. And when you burn the coal, you get a lot of heat. Well, heat will not fit in a wire. It won't make my TV come on. So what they do is they take the heat and heat up water and pressurize and heat it, and they blow this hot steam at a blade, many, many blades in a wheel. That's called a turbine. And you go, and you get the blood gas. See that? Now the turbine is connected to a generator, and a generator has wires and magnets in it, and all you have to do, if you can get the middle of that generator to move, it'll create electricity. So we're going to let the turbine go woo, 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 and that's going to make this thing go woo, 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 and that's going to make electricity, and they're going to send it all over the place and charge people money for it, and that's how they make electricity. That's one way. Now, what's another way that you can make electricity? Nuclear power plants. Now, nuclear power plants, here's what they do. They let radioactive elements come in contact with themselves and neutrons, and they end up undergoing a fission reaction where you actually kind of split atoms. And there's a huge amount of energy that holds the nucleus and atom together, and we're trying to release that, and it's released as heat. What are you going to do with that heat? You can't see my TV with that. I think I'll let the heat up water. And then what? I think I'll let the water turn to steam, push the turbines, turn the generator, and make electricity. Well, that's kind of the same, isn't it? I just need heat, don't I? Yes?
Can the water become radioactive?
Okay, now, I love your questions. I have some details later, but if you're a nuclear power plant, I don't want the radioactive water to hit my turbine. Why not? Because it might need to fix the turbine. And who's going to go in there? So, what they do is they make hot water in certain pipes, and they have pipes with non-radioactive water right next to it. Well, guess what happens? Something gets transferred from a hot pipe to a cold pipe. It's called heat. So your radioactive water, it's hot. I don't want the water to be transferred. I just want the heat to be transferred. So they transfer the heat from one system of hot water with radioactive water to a system of water has no radiation in it, and there you go. Now I got my hot water. And if I need to fix the turbine, I don't have to worry about radioactivity. So the same radioactive water goes back, it loses its heat, now it's cool, heat it up again. Get up again. Yeah, do it again. And a good question, no, they don't use radioactive water. So now that goes back to this question, right? Where I lived, and it was kind of like a Duke Power thing. Why did they build? That cost a lot of money to build that thing, you know that? And it was on Lake Michigan. That's where I lived. So why were they forced to build that? Because they had many, many studies. The Environmental Protection Agency had many, many studies showing that if you take water out of a lake and you start returning it at even 5 degrees warmer, and you keep doing that, you had this many species, and you'll kill a lot of them. You'll kill a lot of species of fish and animals in that lake. So the law is that you were not allowed to return at 5 degrees higher. It had to be almost identical temperature that you got out of. So what they did is they sent the hot water, and they went to a little series, little waterfalls inside the tower. And what happens to hot water when it falls in the air? It cools off. Some of it is steam, right? When you get done, you got cool water. You got cool water at the bottom. Put that back in Lake Michigan. Anyway, so that's what the cooling tower is. Now, on a nuclear power plant, same thing. They have hot water, not radioactive though, remember? And they still have to cool that water to put it back in the environment. Anyway, by the way, this right here, that's where the good stuff is. Now, that right there is built like an arch. Remember physics? They built this like an arch. And that one, engineers said, even if a 747 were to run into it head on, you would not break that. And we don't want people doing that. We don't want people breaking this because that's where the radioactive stuff is. See that? Now, you know what's bad about an arch? What's the weakest part of an arch? Not the outside. The outside is really strong. You can even stand on egg. Sometimes you can stand on egg, not break it. You had a little chick can do what? Arch is very weak from the inside, isn't it? So if you had an accident and you build up pressure in this containment area, then the chance of this blowing up is pretty great. It's not strong with forces from inside. See that? Anyway, we talk about Chernobyl, and you talk about different places, and I will show you at least one of them. I forget the name in Japan. What's the Japanese one?
Oh, yeah, no, there was a plant that exploded in like 2009.
Yeah.
It's,
But anyway, when I saw that, I was so taken because the engineers who had made that plant, I don't think they did anything wrong. Nobody knew that a tsunami was going to come and do that. But they did know one thing. Somehow they hadn't planned for everything, which you can't. But their dedication and their it's like sense of oneness with the people said they knew when they walked in there, the engineers, we've got to contain that radiation or hundreds of thousands of people could die. But if they walked in there, every one of them knew they were going to die. They were going to be exposed to so much radiation. They might do work. They might be able to work for about 10 to 15 hours, but they were going to die. And yet they went in there, one after another after another. That was touching to me. There's no way you weren't going to die, even with your suit on.
it was called Takamura.
Yeah, okay, is that it, Takamura?
I think so.
I'll look it up. Anyway, so this part right here, you ever seen bumper stickers that say no nukes? Well, the author's making a little joke, not joke, but no nukes, no nukes, no nukes. And what does this say? No nukes. No nukes. You should know about nuclear, yeah? All right, anyway, I want to show you a couple more pictures and then we'll move on. Today was actually an intro day. This right here, when you start reading this, you'll hear about this guy named Röntgen. And Röntgen was one of the first people to discover a strange thing happening. Can you imagine that you had, unfortunately, I don't think any of you have ever taken a picture with real film, have you? Have any of you used a camera that used film? Wow, for over 100 years, people knew what film was. And film was a layer of chemicals. Sometimes 3 layers, when it's black and white, 1 layer of chemicals. When it's color, 3 different layers of chemicals. I don't know how they did that. And when light was exposed to that, when you open the shutter, go, take a picture, certain colors would change and you get a picture. And that was and what happened is you take your pictures and then you had this roll of film. Where's my pictures? You had to send them away. And sometimes it took a week. I couldn't wait. A week later, I go to Walmart or somewhere. It was Kmart back then. They had a Kmart. And I go back there and I pick up my pictures. Ooh. So sometimes I had to wait a week, maybe 2, before I could see my pictures. And that was all a chemical reaction that took place, okay? Now, can you imagine somebody who had a photographic plate and he kept it in the dark? I kept it in the dark. And then I had a rock. I found a rock. It's a different kind of rock. And somehow, I'm not even sure how this happened, this rock was in contact with my photographic plate. But later, I developed the plate. I let a chemical reaction take place, and I should be blank. I didn't let any light get to it. You get that? But it showed. The plate showed like, whoa! You must have shined a light on that thing. I didn't. Well, then why would it look like you shined a light on it? And it was this stuff, this radioactivity that was coming from that rock. Now, another type of energy that can come from a radioactive material is X-rays. And anyway, so Röntgen discovers the X-ray, which eventually is used to pass through materials. X-rays are really, really good at hard surfaces. Engineers might use pipes. They might look at pipes and take X-rays of pipes. They don't want to see any micro cracks. Bones. Got a crack? I should be able to see it. X-rays are terrible at soft tissue. Oh, my intestine, something's wrong. Let's X-ray it. That won't do any good. That's soft tissue. But we could let you drink this material that will coat the inside of your intestines. And it'll give off a light. And I'll take a picture of that. And then I can say, oh, look at your intestines, it's got a knot in it. I didn't know that. The only way to find out without opening you up is one of those. So anyway, x-rays are one thing. This is that film I was talking about. Like, what happened? Somebody shone a light on my, no, not really. And then you hear about these people. Becquerel was another one, and then the Curies. And have any of you ever watched that about the Curies? You did? Where'd you see that at? History?
I think in your class we watched like a.
Did you watch one of the videos in here?
Yes.
Okay. So, the number 2. So that had Curies, right?
Yes.
If you look on, is it Netflix? Which one has a series on that?
I think it was maybe History Channel.
One of them has a series called Marie Curie or something like that, and they tell several stories about that. Anyway, that's a neat story also about the Curies. All right, we'll stop there for today, and if you would just start reading this, just start reading your packet a little bit and see if you can get some interest here.